Like millions of people, I watched Derek Muller's Veritasium video on the big misconception about electricity, where it posted a creative thought experiment. He had you imagine zero resistant wires that traveled half a light second in each direction, halfway to the moon and back, to connect to a light bulb 1 meter away. He then asked the following question.
After I close this switch, how long would it take for the bulb to light up?
But then he proceeded to answer a different question, which is how long it would take for any electrical signal from closing a switch to reach the bulb. Although I agree with Derek that the time for the first electric signal to reach the bulb is 1 meter over c seconds, and I agree with Derek that the signal can induce a temporary voltage and current in the bulb, I disagree about the time for the bulb to light. I think that depends on the features of the bulb, the switch, and the battery, and how you close the switch. To explain why I disagree with Derek, this video will be split into 4 parts. First, why the electromagnetic signal is created by closing a switch, but doesn't light the bulb. Second, why the Poynting vector is unrelated to DC circuits. Third, some real-world definitions of potential difference, aka voltage, current, and electric field. And finally, what I think happens when you close the switch in a DC circuit. Ready? Let's go!
Electricity, 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 electricity.
Part 1. The EM pulse from closing a switch. Before I watched Derek's video, I knew closing a switch would create an electromagnetic pulse. And the reason I know that is because I had studied the history of wireless radio and conducted a simple experiment. See, if you close a switch from a battery near an AM radio, it'll create static. See? By the way, the fact that pulses from sparks don't affect the frequency is why FM radio was invented.
Now FM.
So although you could design a system called a coupled antenna, where the pulse from closing a switch would induce a temporary voltage and current in a parallel wire, that's not what lights up the bulb. And you can tell that because it works whether the separate line is connected in a circuit or not, as Derek admitted in a follow-up video.
To illustrate this, Ben added a wire below the circuit that is completely disconnected from it. And what you can see is that its response to the changing electric field is virtually identical to that of the top wire.
A possible flicker from a separate spark is not my definition of turn on the light bulb. And this temporary pulse is not the signal that gives the light bulb power, P equals I delta V. Don't believe me? Imagine if the switch and battery were moved to the far left of the circuit, half a light second away. In this case, do you think that the pulse from closing the switch near a 6-volt battery is inducing a significant voltage and current in the wire a half a light second away? It doesn't make any sense. Or in another example, imagine switching the battery for a charged large parallel plate capacitor that was previously charged by a battery, so same EMF as the battery, and switching the light bulb for a brave person wanting to get shocked. When you close the switch, it'll make an electromagnetic pulse. But do you think that pulse is really what is making our brave volunteer get a terrible, terrible shock? Instead, isn't it only reasonable that our volunteer is going to get shocks when the charges that were on the capacitor actually push charges to flow through the volunteer? And for that to happen, it has to go through the wire. Honestly, the electric signal flowing through the wires is just logical, which brings me to Part 2, the Poynting vector and DC circuits. When I first watched Derek's video, I was very confused as to why he was so insistent that the electromagnetic pulse moving radially from a switch had anything to do with the electrical power in the wire. But then I learned from Derek's video and the responses to it that it was not Derek's fault. He and many other advanced engineers and scientists were taught a confusing model of electrical flow involving the Poynting vector. This model puts the electric power outside the wire, not in it, and it was promoted by a man named John Dave Jackson in the mid-1990s. I went to graduate school in physics and then engineering and then physics again around that time, but I guess my teachers were out of date because I don't remember learning this in school. Anyway, the main tenet of Jackson's model is that as soon as the switch is closed, the battery induces an extra set of static charges on the surface, and the electric field from these external charges maintain the potential around the circuit and assure the confined flow of current.
The main thing I like to think about the battery doing is maintaining this distribution of surface charges.
As in his video, here Derek explains that there is a gradient of seemingly static charges only on the surface of the conductor, and the density of charges inside the bulk of the wire is uniform, with number of electrons and protons being equal. So the charges inside the wire don't push each other to move, because the conductor is electrically neutral there, and the net force on charges from neighboring charges is zero. Derek claims it is the surface charge gradient that creates fields inside the wire, pushing charges forward.
But here's the thing. Static charges don't affect the electric field in the conductor. That is what Michael Faraday discovered in 1837 when he built a cube or a cage of metal and found it protected him from the electric field from charges on the surface of the cage, though all the time the outside of the cube was powerfully charged and large sparks and brushes were darting off from every part of its outer surface. There's a lovely video about this made by the Nobel Prize winner Sir Lawrence Bragg from the 1960s.
Strands of silk are forced away from the cage, but the charge has no effect at all on the girl inside. Faraday performed this experiment. It showed that there is no electric field inside a hollow conductor. When the girl puts her head through a hole in the cage, the tinsel of her crown and wand are affected, but she is safe, as long as she touches nothing outside it. To render the cage harmless, it must be discharged.
In fact, Faraday made up the whole idea of electric fields specifically because conductors shield you from static charges. In addition, Richard Feynman said that this theory of the Poynting vector is obviously nuts in his 1962 lectures in physics, which it is. I mean, check out the word salad that John Henry Poynting said about energy in DC circuits in his seminal paper of 1884. And keep in mind, heat is a form of energy. Quote, "It seems then that none of the energy of a current travels along the wire, but that it comes in from the non-conducting medium surrounding the wire. That as soon as it enters, it begins to be transformed into heat, the amount crossing successive layers of wire decreasing till by the time the center is reached, when there is no magnetic force and therefore no energy passing, it has all been transformed into heat." I agree with Feynman when he declared, "How absurd it gets." Note that I'm not complaining about Derek Muller or anyone else who believes what they read in textbooks and peer-reviewed papers. That's what we're supposed to do. However, people like Jackson who read or even heard how tentative Feynman was about the Poynting vector and still pushed it to be in all textbooks earns my everlasting ire. Add that to Feynman's influential philosophy. The physics is a series of facts, and if you don't like it, well, you can just go somewhere else. And I have a lot of irritation towards both men. Don't believe me? Look at what Feynman said about education.
If you want to know the way nature works, we looked at it carefully. Look at it, that's the way it looks. You don't like it? Go somewhere else. To another universe where the rules are simpler. Philosophically more pleasing, more psychologically easy. I can't help it, okay? If I'm going to tell you honestly what the world looks like to human beings who have struggled as hard as they can to understand it, I can only tell you what it looks like, and I cannot make it any simpler. I'm not going to do this. I'm not going to simplify it.
I believe the opposite. Like Michael Faraday, Nobel Prize winners Sir William and Sir Lawrence Bragg, Sir David Attenborough, Carl Sagan, Dame Nancy Rothwell, and the lovely Mr. Fred Rogers. I believe, as I said in my What I Believe video, that
I believe that everything, and I mean everything, can be taught to children. And I believe in you. I believe you can understand the world. I believe you can make this world beautiful.
It is strange to me, but several people told me that my words sounded angry, when really what I thought I was expressing was passionate belief. And Feynman's words were considered funny, when to me they sounded mean and dismissive. Anyway, it was due to Feynman's attitude towards education being so contrary to my fundamental beliefs that I started discounting all of Feynman's work, which I shouldn't do, as much of it is very deep, clever, and well done. However, his material on the Poynting vector seems to me to be, well, nonsense. I'm putting a link to the audio recording of Feynman's lectures on the Poynting vector, as well as the print version, and you can listen and read for yourself if you wish. Please tell me if I'm missing something profound. Now that brings me to part 3, defining terms, voltage, current, and electric field. Let's start with voltage or potential difference. Voltage is not a tension or a pressure. It's an energy per charge. That is why the units of volts are equal to the units of energy per charge, joules per coulomb. There are a whole host of types of energies, but they generally fall into 3 categories. Potential or stored energy, where the object is static. Kinetic energy, where the object is in motion. And thermal energy, when the atomic or subatomic particles are in motion. Sometimes physicists combine kinetic and thermal into one category, but I find that confusing. Anyway, let's start with the energy stored in a parallel plate capacitor. Here is how this works. If you have charges on 2 plates, then there's a potential energy in the insulating material between the plates, which depends on the charges on the plates Q, the distance between the plates D, and inversely on the area of the plates A, and what Faraday called the dielectric constant, which is now represented by the Greek letter epsilon. Delta V equals QD over A epsilon. Note that the open switch works the same way, except the area is so small that the charges on it are minimal. How about an electric cell or a battery? Battery cells are very simple. They have 2 different metals in either a strong acid or a strong antacid, or alkaline. And the chemical reaction happens until the negative electrode has too many electrons and the positive electrode has too many positive ions, or atoms missing an electron. These charges arrange on the surfaces of the metal until the potential energy of the charges on the plates equals the chemical potential energy of the acid or antacid. If you close a switch connected to a battery, then it will flow in one direction between the electrodes in what is called direct current, or DC. This is confusing, as we say that the current flows from positive to negative, when what is happening is that the electron flow goes the other way. The reason it is confusing is because of how it is historically developed. See, in 1733, a French nobleman with the elegantly cumbersome name of Charles Francois Cisternet du Fay described how there were 2 types of electricity: resinous, from rubbing wax or resin, and vitreous, from the Latin word for glass, from rubbing glass. Dufay's work then inspired a crazy German named George Matthias Bose to declare that he was an electric wizard and started entertaining everyone with his crazy electrical experiment. According to a book written in the late 1800s, the year 1742 probably marks the beginning of this singular and sudden interest in things electrical, which arose in Germany, and which swiftly reached the stage of feverish enthusiasm. One of Bose's favorite experiments was to electrify himself so his hair would stand up, and then use a spark from his bare hand or from a sword to light alcohol on fire. Now, this experiment seemed like so much fun that I had to recreate it. Let me show you. This is a very important experiment, so let me go over it in detail. First, he had an assistant spin a wheel to cause the glass tube to spin quickly. Another assistant rubbed the sphere with his bare hand to charge up the sphere. Bose then held a large metal tube against the glass sphere. He was standing on an insulating stand until he collected quite a lot of charge. Then, once he was all charged up, he would point at a container of alcohol with his finger or a small sword, and a spark would leap to the alcohol and light it on fire. Let's watch that again in slow motion. All good. By 1747, Benjamin Franklin joined in on the fun, and he wrote a friend, "For my part, I never was before engaged in any study that so totally engrossed my attention and my time as this has lately done. My friends and acquaintances come continually in crowds to see them. I have, during some months past, had little leisure for anything else." Franklin was the one who decided that rubbing objects didn't create electricity, merely moved it, when he made an electrical machine with a broom or silk rubbing against the glass. As brooms pick up dirt, he assumed it picked up the electrical fire, which he called positive, and assumed that the glass had a lack of electrical fire, which he called negative. This debate continued into the 1800s when my favorite scientist, Michael Faraday, named the positive electrode, where he assumed the current was coming from, the cathode, and the negative electrode, where he assumed the current was going to, the anode. Terms we use to this day. I go into the history and physics of the cathode ray tube and the CRT television and podcast with Dave Jones of EEV blog fame if you're interested. Anyway, it wasn't until 1897 when an Englishman named Joseph John J.J. Thomson discovered that the cathode ray tube was making a stream of negatively charged particles irrespective of what material the cathode was made of. And these particles were quickly called electrons. By this time, engineers were used to saying the current flowed from positive to negative, so they basically just put their fingers in their ears and said, no, we're still going to say the current flows from positive to negative. Don't blame me, blame Franklin. There is this hilariously geeky comic from the wonderful site XKCD about how an electrical engineer went back in time to stop a robot apocalypse, but instead wasted his time making sure that the glass got the positive charge. Anyway, you might wonder what this has to do with the electric field. And to understand that, you need to know that the electric field is a measure of the force per charge, which is why it is measured in newtons per coulomb. Using Clausius's law of work-energy equivalence, we can say that without outside forces, work equals force dot distance equals the drop in energy. Or in terms of field, work equals QE dot D equals Q delta V, where delta V is the drop in potential. Or E dot D equals delta V. If the electric field is constant in, say, the y direction, then you get EY equals delta V over delta Y. If the electric field is not constant, then you get EX equals dV dx, EY equals dV dy, and EZ equals dV dz, which is usually written as E equals the gradient of V or the negative gradient of phi, where delta V is the drop in potential and delta phi is the change in potential. Now we are finally ready to solve Derek's physics puzzle. Part 4. What happens in a DC circuit? Like I said, a switch acts like a tiny parallel plate capacitor. When you close the switch, it creates a small electromagnetic pulse and two signals, one pushing the charges and one pulling them. However, it takes several cycles for it to reach its steady state. As the work is the charge times the change in voltage, W equals Q delta V. The power, which is the time derivative of the work, is the current times the voltage, or P equals I delta V. If you have a DC system in steady state, then you can use Ohm's law, delta V equals IR, to get that the power is P equals I delta V equals I squared R, which is Joule's power law for DC systems, as Poynting mentioned way back in 1884. This is why I say the power is dependent on the current in the wire and the voltage difference across the wire. Now, in this system, you will have microcharges on the surface. Thank you, Dr. Eric Michelson from UC Davis, for working that out for me. But they don't matter, because you can change them by moving a charged balloon next to it or moving the light bulb closer to the battery, as Derek admitted in a follow-up video.
Consider that the electric field of the battery is much larger close to the battery. So if its field were really what's pushing the electrons around, then if you brought the light bulb close to the battery, then the bulb would glow much brighter, and it doesn't.
That's why I think the answer to Derek's puzzle is E. None of the above, as we can't know how long it takes without knowing the properties of the bulb, the switch, the battery, and how long it took you to close the switch. Now, just because I disagree with Derek's conclusion does not mean that I have anything but the utmost respect for him and his channel. Science is not always correct, and pseudoscience is not always incorrect. In fact, real science almost always has little mistakes in it, because some things don't stand the test of time, and scientists are human, and we make mistakes. So there's often little mistakes in them. And pseudoscience almost always has little nuggets of things that aren't correct. Otherwise, they wouldn't be believed. The difference is real scientists are trying to clarify the subject, and pseudoscientists are trying to obscure the subject. Real scientists should try to present their mathematical models in a common language as fully and clearly and definitively as in mathematical formula, neither above nor below the truth. as Faraday wrote to Maxwell in 1857. Real scientists are not afraid to ask questions and disagree with authority. Real scientists welcome debate and develop their ideas with interactions with others. Real science can be used for other situations besides just the one being presented. Real science comes from a river of ideas and does not leap completely achieved from the brain of the scientist, like Minerva emerging fully armored from Jupiter's head, as Marie Sklodowska-Curie liked to say. Pseudoscience, on the other hand, is presented as facts, which is not open for debate. It must be swallowed whole and only can be understood by certain elevated elite individuals. Pseudoscience can be presented as crazy and clearly nuts, but you are still required to believe it against your better judgment because of the authority of the presenter, rather than the usefulness and logic of the theory. In other words, real science makes you think, and pseudoscience makes you obey. And I gotta tell you, Derek's video made a lot of people think very deeply about electricity. His video is the one and only reaction video I've ever made in my entire time as a YouTuber. The fact that I've spent so much time on it is symbolic of how much I admire Mr. Muller and his channel. I would be more than honored to discuss this material on his channel or any other established YouTube channel. I'm sure some healthy debate would help me clarify my ideas and find any mistakes I've made. In the meanwhile, I have over 100 videos on all sorts of topics. For example, I have a video where I derive all 4 of Maxwell's equations from simple concepts in under 35 minutes, which I'm very proud of. I have a lot of videos about the history of wireless, as well as spectroscopy, the history of transformers, and 3-phase electricity, and more. I also have a bunch of videos on Max Planck, who I admire greatly, both for his science and for his morals. Werner Heisenberg, whose science is great, but whose morals were not, in my opinion. In addition, my first book, The Lightning Tamers, is out and available on Amazon, from your local bookstore and from your local library. And it is about how electricity developed and ended up in your home. Big thanks to my patrons. And as usual, stay safe and curious, my friends. Bye.